Today we're going to take a look at exponential functions, specifically e. Okay, so we're looking at anything to do with e today. A couple of things I want to remind you of, just a couple of exponent properties, not necessarily about e, but just exponent properties in general. If we have e to the a times e to the b power, that's e to the a plus b. Remember, when we have multiplication, we add the exponents as long as we have the same base. And then also, if we have division, let's say we have e to the a divided by e to the b, then that's e to the a minus b. That's just to kind of refresh, make sure we remember those properties in case we have to use them when we're simplifying something down. Sometimes we might be simplifying an integral before we take it. Sometimes we might be simplifying an answer when we get it. So just keeping those properties in mind can be helpful. Also, just a quick one in case we ever end up with this. Remember, natural log of 1 is 0, and natural log of e is 1. Again, those can just be useful when we are evaluating either a definite integral or if we're maybe plugging in for a derivative value if we've taken a derivative. All right. Let's get into the big ones for today, which starting out are derivatives. Let's look at derivatives of e. Okay, so derivatives involving functions with e. The derivative of e to the x is e to the x. The derivative of e to the u, where u is some function of x, is u prime times e to the u. Okay, so a lot of times people will get very confused when they see this, but this is true. The function e to the x grows at the same rate of the actual function. Okay, so the derivative of e to the x at any point is equal to e to the x at that point. Now, it gets a little bit different when we have e to the u, because we do have to multiply. It's like chain rule, right? Derivative of e to the x is e to the x. So derivative of e to the u is going to have e to the u, but we have to remember to multiply by the derivative of the u prime. Okay, so let's take a look at some examples. How does this work? Let's say we have, start with something easy. Let's say we have e to the 2x plus 1. Okay, derivative. Our u is 2x plus 1, so we're still going to have e to the 2x plus 1. And then we have to make sure to remember to multiply by the derivative of the u. Derivative of 2x plus 1 is just 2. So our derivative is 2e to the 2x plus 1. And again, of course, we can use this in any way we need to. We can use this to find the slope of a tangent line. We can use this to find whether functions are increasing or decreasing at certain values. So these can still be used in the exact same way we've used derivatives before. Let's kick it up a notch. Let's try one. What if we have e to the 2x times natural log of x? Notice here we've got e to the u because it's a 2x instead of just an x. We also have a product rule because we're multiplying e to the x and natural log of x. So let's see what this would look like if we take the derivative. Product rule, we start with first one times derivative of the second one. Derivative of natural log of x is 1 over x, plus the second one, natural log of x, times derivative of the first, e to the u, e to the 2x, times u prime, 2. So let's just rewrite this. We would have e to the 2x over x plus 2e to the 2x times natural log of x. I wouldn't try to simplify down any more than that. Even if you factor out something, you're still going to have a 1 over x, so I wouldn't worry about that. I would leave this answer as is. You may also have functions where e is inside and part of the u. What if we have natural log of 1 plus e to the 2x? So we're taking the derivative of a natural log function, but within that, we're also going to have to take a derivative of an e when we do this. Let's take that derivative, okay? Derivative of natural log of u is u prime over u. So we're going to have 1 plus e to the 2x on the bottom. Now we need to take the derivative of 1 plus e to the 2x. Derivative of 1 is just 0, so that's gone. Derivative of e to the 2x is e to the 2x times derivative of 2x, which is 2. So our final answer for derivative would be 2e to the 2x over 1 plus e to the 2x. All right. Let's take a look at integrals involving e to the x. And we'll start with the easy basic rule. Integral of e to the x dx is e to the x plus c. Okay. If we have a plain e to the x, we love that because that's very easy to work with. If we have the integral of e to the u du, that's e to the u plus c. And again, the big portion is making sure we recognize what is the u and what is the du. So a lot of times we're going to have to multiply by a constant because we may not have the exact same du as we have. Let's take a look at some examples. Let's say we have integral of 4x times e to the negative x squared dx. Okay. Our clue that something is different is the fact that we have e to begin with. And then you want to look at your exponent in e to figure out what makes this even more different is that we don't have a plain e to the x, we have e to the negative x squared. The one nice thing about these is that usually whatever's in your e exponent is your u. So our u is negative x squared. Our du would be negative 2x dx, the derivative. So let's rewrite in terms of u. Okay, e to the negative x squared, that's easy, that's e to the u, right? Now, we have 4x dx. Our du is negative 2x dx. So in terms of du, we have negative 2 times that, right? We have a positive 4x, and so we have negative 2 times the du. I'm going to put that out front because it's just a constant. Let's take that integral. Negative 2 is a constant. Integral of e to the u du is e to the u plus c. So let's plug back in our plug back in our u, excuse me. So negative 2e to the negative x squared plus c. And notice you could quickly take that derivative if you wanted to. Negative 2 times e to the negative x squared times derivative of what's up top, negative 2x. That would give you positive 4x e to the negative x squared. So notice that you could quickly check, does this work to give me that original function I was taking the integral of? And yes, it does. All right, let's put in some trig. What if we have the integral of sine of x times e to the cosine of x dx? Okay, the fact that we have an e tells us this is a little bit different. Not only do we have an e, we have e to the cosine of x. So our u in this case is going to be cosine of x, which would mean our du would be negative sine of x dx. Okay, let's rewrite this in terms of u. E to the cosine of x, that's e to the u. Now notice we have sine of x dx, which is the same as our du except for the negative, right? So we just call this negative du. So when we take the integral, we have a negative. Integral of e to the u du is e to the u plus c. Plug back in our u, so we have negative e, the cosine of x, plus c. And again, you could take that derivative really quick to make sure that it works, and it does. All right, let's try another one that's a little bit different. What if we have integral of 2e to the x? Oh, it doesn't look like an e. Let's fix that. 2e to the x over 1 plus e to the x. Now, we cannot divide each term. because we have an addition on the bottom. If these were flipped, we could divide each term by 2e to the x. We can't do that here because we have an addition on the bottom. So our whole denominator is 1 plus e to the x. What I would think about here, though, is if we think of the bottom of this function as our u. So if that entire bottom is u, 1 plus e to the x, our du, the derivative, would just be e to the x dx. So let's try rewriting this in terms of u. The 1 plus e to the x on the bottom, that's 1 over u. Then we're left with 2e to the x dx. Okay, our du is just 1 e to the x dx, so we have 2 times the du. And again, it's a constant, so I'm just going to put it out front. Okay, here's a constant. Integral of 1 over u du, well, that's our natural log rules. That's natural log of absolute value of u plus c. So let's plug back in our u. 2 times natural log of absolute value of 1 plus e to the x plus c. So notice on that one, our u was not actually the exponent for the e. Okay, and notice we just had plain e to the x's there. So our u was not the exponent of the e. In this case, our u actually had to do with e, and we were doing a regular u substitution problem with natural log. Okay, again, this is where kind of having that intuition about what rules to use can come into play. Let's try one more. It's going to be kind of the same deal in that we're not necessarily looking at the exponent of the e as our u in this case. In this case, take a look at what we've got. E to the x times cosine of e to the x dx. Now, normally, if we have a cosine function, if it's cosine of x, we know that integral. But the difference here, we have cosine of e to the x. Okay? So what if we make our u e to the x? Our du would then be e to the x dx. So if we rewrite this in terms of u, well, the cosine of e to the x, that portion is cosine of u, right? That leaves e to the x dx, which notice is exactly our du. So now we have the integral of cosine of u du. Okay, think back to your rules. Integral of cosine is just a regular sine, positive sine of u plus c. Let's plug back in our u, sine of e to the x plus c. Okay, and again, we can use this in all the other ways we've been using integrals. We can find average value. We can find an original function. Maybe they give us the derivative and an initial condition, so we can work backward and find the original function. We can use these derivatives and integrals in the same way that we've used all of our other derivative and integral properties before, except now we have the capability of using e with those. Okay.